So, as the introduction said, my own background is predominantly in mathematical biology, both theoretical ecology and environmental science. In the last few years, I've drifted into doing some work with sports scientists, mainly here at UTS. And in getting into this field, there was a few, I think it's safe to say, eye-opening findings, at least to me, practices which I'd not seen in other applied fields. And so I'm going to keep this talk not too technical, but with a bit of an overview of some of the peculiarities and unique features of working with these kinds of data sets and in this kind of application, and hopefully sell a few of you on some of the opportunities for work in this area and a great potential minefield of future work and future collaborations. So as I started to write this talk the other day, I just wanted to sort of start by thinking of some of the most highly cited statisticians in Australia. So I did a little bit of a mental test. I probably mentally produced about 30 names from my head of people I thought would be people who would be highly cited. And I had the arbitrary definition of having at least 40,000 career citations, which is, by most metrics, quite a high bar. Now, I'm not a deputy vice chancellor, so I don't confuse number of citations with research quality or anything like that. But in doing so, by the time I Googled a lot of these people, I came up with 8 names that I could confirm of people, broadly speaking, in stats, so including biostats, statistical geneticists, and people like that. So there we go. Those were the 8 people I managed to, I think, confirm and hit, at least according to Google Scholar, which is one of the more generous ways of counting citations. Those 8 faces. Now, I'll leave this as a little challenge for you to actually put names to those 8 faces. Now, some of those, if you're working in a statistics department, I'm sure some of those are very recognizable. But I also think they will not all be that recognizable. So I just put up the list of names. They are, and that is in order. So if you work across the top row is the top 4 on that list, and the work across the bottom row is the bottom 4 on that list. I can't really ask anybody to shout out on an online talk, but is there one of those names which sticks out to anybody's mind as being less well known than the others? Because amongst that list, there's fellows at the Academy, there's Pittman medalists, and there's one, I'm just seeing something emerge on my screen. There's somebody actually answered this in the comments. There's one which is probably less well known, which is on the bottom row, 3rd across, Will Hopkins. So certainly for most people working in statistics, people like Kerry Mengus and Noel Cressy would be within the field household names, whereas Will Hopkins probably less so, but he is at this 40,000 career citations level. So it seems strange for somebody to be a statistician working in Australia who's relatively off the radar within their own field. So if I just focus in on Will Hopkins, and he works at Victoria University in Melbourne, and what it is that sort of brought him to that level of citation. And he really has worked almost exclusively in sports science and has developed this technique, which is very, very widely used in sports science, particularly studies out of Australia and New Zealand, which was always called MBI, magnitude-based inference. He's lately rebranded it as MBD, admitting it's not sort of inference in the same sense a lot of people in statistics mean that term, but using it as a decision-making tool, so MBD. So I'll use MBI and MBD basically interchangeably. You will still hear both terms, although the originators of this technique now favour MBD, but a lot of people are still stuck in the past with MBI. So if I just look at the information about Will Hopkins on the university website, he has his own journal site, sportsci.org, devoted to research, resources, and conference reports. He's best known for rejecting statistical significance and replacing it with a clinically and practically more relevant method of inference based on uncertainty in the magnitude of effects. So I think it would be a waste of everybody's time here to go through the age-old debate of the limitations of p-values and over-reliance on 4.9% as a p-value proves something, 5.1 as a p-value disproves something. There's no point in going down that line. But basically, as a rejection of a lot of that classical null hypothesis testing, and particularly for some of the quirks of sports and exercise science data, it developed a lot of resources on the website which are freely available to do things statistically differently. And obviously, this has been, at least from a citation point of view, a great success. So what is there specific about sports studies that require their own branch of statistics? Not frequentist stats, not Bayesian stats, but a whole other MBI or MBD thing. Well, the primary feature is that sample sizes are typically very, very small by most measures, because most studies in this field are looking at the elite level, so looking at the very top level of the professional sports industry, of which there are very few people. And of course, to do these evaluations of dietary changes or training changes requires longitudinal studies of which people drop in. There's a whole load of other factors. Maybe people get injured, maybe people don't keep up the same intensity. So the actual data sets will be very noisy and based on very small numbers. And by very small numbers, I mean often single figures as a control group and single figures as a treatment group. So by what most people would think of in terms of dealing with applied stats problems, very, very small sample sizes. And so, of course, even when effect sizes appear large, if you've got a noisy data set, even if you would estimate the effect size to be large, with a lot of noise and uncertainty around that, you would often get these things whereby they would actually fail to reject a null hypothesis under a classical hypothesis test. So a lot of people would be saying, the evidence is suggesting this, but just because the sample is small and noisy, we can't be certain, we can't reject a zero effect. So very often, classical methods would not detect changes, even when practitioners, people working in the field, would say, yeah, maybe the evidence wasn't strong enough for statistical certainty, but I knew that was working. So MBI and MBD works slightly differently. It actually isn't a hypothesis test. It's at least two hypothesis tests. It's assigning a threshold below which a treatment, if the impact is more than some negative thing, it would be deemed harmful. If it's more than some positive thing, it's deemed beneficial. And if it's between them, it will be deemed trivial one way or the other. So it's actually multiple hypothesis tests at the same time. That isn't how it's framed, but that is actually what mathematically it is. And then qualitative labels are assigned to this based on estimating what's the probability it's beneficial, what's the probability it's harmful, and then making some sort of reasoned decision. So that's why in some ways the newer label of MBD is probably more accurate. It is a decision-making tool rather than inference in the way that most statisticians would deem an inference problem. And the real joy of the sports sci site, and the reasons I think it's become widely used, is that everything is freely available as very easy to use Excel spreadsheets. So if you've done some stats in any other package, you get a p-value, you get an estimated effect size, a Cohen's d for the effect size. You can just drop these numbers in there, press a button, and it'll give you qualitative labels out of this. This was really my first experience dealing with MBI. Was I read a paper which I was sent by a collaborator of mine, and their conclusions were all, I've drawn the conclusion this is probably beneficial, or this is very likely beneficial, and these weird sort of qualitative labels, which I thought were quite confusing. By the time I sort of dug deeper, I realized that they were not the author's own quirks, that these were very standard in the field, thanks to the work or the MBI technique. Transitions. Yeah, so I'm not going to go into the limitations of p-values. I think everybody's very familiar with those. But the argument being that the magnitude-based way is a way of sidestepping that. So using some of the ideas of frequentist stats and getting a p-value and also getting an estimated effect size, but also identifying where you have things which are likely beneficial, which a frequentist classic null hypothesis test wouldn't necessarily see as significant. So you would get these ranges on there. So you can see there is the points on the, based on the effect size. So the point in the middle of those, everything's symmetric. So in this world, everything's Gaussian unless you're certain it's not. So they would estimate an effect size and some measure of uncertainty around that. And based on where it fell on this scale of completely arbitrary definitions of where the borderline between trivial and beneficial is and where the borderline of trivial to harmful is, and then make these labels of very likely harmful, possibly trivial, probably trivial, depending on how much of that range fell into each category. So philosophically, the argument of this being that if you had, and I'm deliberately using modelled terminology here, but if you had some training regime here and your belief, and I'm using the word belief, I'm not using confidence interval or anything like that. If your belief was that the effect of this particular treatment would be to change your time for running a marathon between -9 minutes, i.e. a 9-minute improvement, and +1 minute, i.e. a 1 minute sort of worsening. A classical hypothesis test would say that if that was your confidence interval between -9 and +1, you couldn't rule out 0, so you wouldn't say that there was any reason to believe that this treatment was beneficial. However, a coach might say between -9 and +1, there's a lot more of that range, even if it's not symmetrical. There's a lot more range negatively than positively. The middle of the range would be about -4 minutes. So even if it's not symmetrical, they'd get a look. If it doesn't cost anything, it's not doing any harm. It looks like it's more likely to be beneficial than detrimental, so I'll give it a go. That sort of philosophically is where MBI comes from and why it sort of come to the fore. The problem is that as this has become more and more high profile and the 40,000 citations has come, is that as it started to hit the statistical mainstream, as, to be honest, any technique in any research field, it deserves to be hit the scrutiny of peers in the field. And a couple of years back, when's the date on that? May 18. A blog post on 538, the Nate Silver site, really kind of kicked this off of how shoddy statistics found a home in sports research. This was largely building on the work of a woman at Stanford, Christian Sainani. If you're interested in the technical details of the limitations of MBI, I'd strongly recommend the video, which is actually linked through from that 538 article, in which it's 50 minutes long, but she goes through a lot of the stuff, looking at rates of false positives and things for this. But since then, it sort of hit mainstream as well, and the Sydney Morning Herald article at the time quoted Alan Welch saying that if you use MBI, they're claiming to have found effects that are very likely not real. If you're familiar with the Twitter handle at stat modeling, that's Andrew Gelman, whose position scientists should spend more time collecting good data and reporting their raw results for all to see, and less time trying to come up with methods for extracting a spurious certainty out of noisy data. And I think that gets to the core of a lot of critics of MBI's issues, the fact it is largely a technique for mining noisy data to find results in. And lastly, got a quote from the president of some obscure arcane society, who suggests that if he were ever to get a paper to review using MBI, it would be just rejected straight away and told to redo the analysis with other methods. So we've got this weird sort of dichotomy between a technique which is in many ways, or certainly has been for the last decade, largely seen as a gold standard of statistical methodology within the field, which by the time it's hitting sort of more mainstream statistics, Adrian Barnett, Andrew Gilman, Alan Welsh, they're really kind of very critical of it and seeing its limitations. Now, part of the problem is that although it's been developed for these small data sets to try and find results find weaker evidence, the problem is that when it's being criticized, the developers and its disciples haven't done a very good job defending it, in the sense they've come out and made great sort of claims published on the sportssci.org website themselves, claiming it's been vindicated and validated, and pretty much accusing people like Alan Welsh of not knowing anything about statistics and blah, blah, blah. Using things like outperforms other techniques, even claiming that it's got lower type 1 and lower type 2 error rates, which I'm pretty certain most people here would think is statistical alchemy, finding more positive results while also generating fewer false positives and things like that, which simply is not what it's doing. They've also garbled a lot of frequentist and Bayesian terminologies. They've sort of dug deeper to defend it. Now, I would say the most major technical flaw with it is that it isn't really frequentist and it isn't really Bayesian. It's a bit of one and then it chooses to be the other. When you look at those intervals and where it's sort of plotted those symmetric intervals for the effect size and uncertainties, it really developed them as confidence intervals and interpreted them as Bayesian credible intervals. It sort of seemed to change midstream what it was actually doing. And the argument of a lot of that seems to believe that if you've got a 95% confidence interval entirely within the trivial range, then you can say you're 95% confident that that's trivial, which is of course not what a confidence interval is doing in the first place. So it's got a lot of technical flaws, as the Christian Sainani video will really sort of point out in better detail than I've got the time or the will to do right now. However, if you'll excuse me being possibly hypocritical here, it's not completely without merit if you accept it as what it is. If you accept it as entirely, this is a way of dealing with small sample studies and also dealing with ones where you've got very skewed risk rewards. If you kind of go, look, this thing is definitely not going to be doing any harm, may or may not be beneficial, but if it's at worst a waste of time or a trivial amount of effort or a trivial amount of money might be beneficial, then you can use it as a reasonable decision-making tool. But the problem is you have to admit that that's what you've done. If you've lowered the bar of the burden of proof, you can't then come out and sort of criticize what I would think of as more mainstream methods for saying this has outperformed them. It's only outperformed them in the sense of lowering the burden of proof, so you can claim that something has been validated or vindicated, when in fact you've just simply moved the goalposts on what is and isn't proof. So if you admit what it is, a watering down of sort of scientific proof, which you could argue is necessary for small samples and is justifiable in certain contexts. If you think of a sporting context, if you're thinking of a change that if you think your athlete's going to come fourth in the Olympics, this thing might shove them up a place, might shove them down a place. The difference in coming fourth and coming fifth is probably not very much. The difference between coming fourth and finishing third or better for a medal might be quite sizable. So you've got these skewed payoffs and you're pretty confident it's not doing any harm. Is it that bad to lower the burden of proof? Maybe, maybe not. But the issue is about it's not comparable to other methods. And so some of the defenders coming out with these spurious claims hasn't really helped its reception. And indeed, if you look at the website as well, sportsci.org, there's a lot of spreadsheets there to help you calculate sample sizes for things. And as the Christian Sainani video shows, their sample sizes are actually ones that maximize your chance of a positive result, so maximize your chance of a type 1 error, even if you've got no effect of the treatment. So there's a lot of limitations there, but it is, of course, a widely used tool, and it does have some merit if you admit what it is. And I've will shamelessly plug a preprint I've got, which is up on archive, looking at this within the context more of decision theory than in stats, but looking at this as ways of evaluating multiple hypotheses, potentially at multiple different significance levels, and showing what it might actually be doing, rather than digging in deeper with misusing Bayesian terminology. Now, that's not the only kind of attempt to move forward in this field. There's a lot of work, particularly coming out of QUT, mainly Chris Travandi and also Kerry Mengus and Paul Wu and people like that. I've been pushing a lot of more classical Bayesian methods as alternatives to MBI within the field. Now, these have been a few excellent papers, which have been, I would say, disappointingly not as well picked up as they might be, because these have sort of stayed mainly within, one was in PLOS One rather than in a sports science thing. So they really haven't quite had the citations I would say that they deserve. But there are efforts from statisticians to engage more broadly and bring what I would think of as mainstream statistical methods to the field. So I'll move on from MBI or MBD to go to the exact other extreme. So I wanted to pitch this talk very much as one of opportunities, so limitations of what's in the field, without being too critical. However, I will suspend my not being too critical to be hugely critical of a study here, which is problem keeping things entirely in-house, so not having any statistical background beyond the sort of cursory undergraduate stats that's in most science degrees, and often just applying routine statistical tests, whether they're appropriate or not. So if you look at the AFL's concussion working group, there's nobody whose primary research field is statistics, and that includes biostatisticians and things, because medical research schools tend to have people with expertise in biostats. The AFL's concussion working group has absolutely none of those. Now, ordinarily, that may or may not be an issue, but if we look at some of the evidence that's been published, I would argue it's monumentally an issue. So I'm just going to start with the conclusion of a paper. The conclusion of this paper, which is the keystone of the AFL's concussion protocol evaluation, is that the current study demonstrates that using the existing blah, 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 no increase to injury rates following return. So this is looking at players who've had a concussive injury and then looking at their rate of injury after returning to play following concussion. So looking at whether or not people who've had concussion are more prone to future injuries, whether that's future concussive injuries or whether that's other injuries, whether they are simply suffering lingering effects and more prone to other injuries. So if you're looking to compare whether or not a group of people who'd had concussions had injuries at different rates to people who hadn't had concussions, you'd be looking at some sort of ratio of rates amongst the two groups. And your null hypothesis would be that the rates of injuries for the two groups was the same. So the ratio of the rates between the two groups would be 1, and you'd be trying to gather sufficient evidence to reject that null hypothesis. And this is the data set on which the whole thing rests. Now, firstly, I cannot for the life in me fathom how out of 4 years of data of every AFL game, they managed to whittle it down to just 29 injuries in the whole study. But nonetheless, they concluded that the rate of injuries to people who had previously had a concussion was 7.25 injuries per 100 games. And for people who hadn't had a concussion, 3.25 injuries per 100 games. So the ratio of those two rates is more than twofold, nearly 2.25 times, 2.23 times. However, because the confidence interval around this is 0.93 to 5.04, which still contains 1, they're very proud to say that because they can't exclude 1 being the ratio, 0.93 to 5.04 being the failure to accept the null hypothesis, so failure to reject the null hypothesis that the ratio of the rates is 1, is the same as, if I quote the conclusion, the study demonstrates no increase in injury rate. Now, if you're returning a point estimate of around 2.25 times the rate, it at very least warrants further study rather than saying that you've demonstrated it. The reason I'm quite happy to be a bit more critical of this is the authors also forgot to declare in the declarations the funding from the AFL for this study. But anyway, that's also some of the exclusion criteria were interesting in the sense they excluded players who were so badly concussed they never played again. They were automatically excluded from this. But I think the most interesting finding is the following, which is looking at cognitive functions for players who have and haven't had, for players who have had a concussive injury. So there's two different tests there. Let me read the thing, DSST, digital symbols substitution test, and TMTB, a trail making test, part B. So if we read the caption to that table, it says that improvement in the DSST score is indicative of improved cognitive function, and a decrease in the time, the TMTB time, is indicative of improved cognitive function. And they were checking people who'd been concussed by looking at the mean change, which was players were tested on these two cognitive tests pre-season, and then if they had a concussive injury, they were tested again before they were allowed to return to play. The interesting thing about this is it actually shows that concussed players had higher cognitive function after their concussion than they did in pre-season, which is interesting. It may actually be true. Of course, it may be that if people are tested pre-season and then tested multiple times, including after their concussion, there's a time effect. But in which case, the obvious thing is that you would need a control group to say, okay, the people who suffered a concussion in the middle of the season scored better on these cognitive tests. So how did people who didn't sustain a concussion in the season do compared to their pre-season scores? Unfortunately, that control is nowhere listed. So if you actually want to improve your cognitive function, try getting smashed in the face, seems to be the advice of the paper, which as a piece of applied statistics, to not include a control group for players who'd never sustained a concussion seems an interesting choice. So I would just say about these sort of studies as an opportunity for people with experience, particularly people who've worked in biomedical evaluations, to actually get involved and actually bring a little more expertise, because this is published in the American Journal of Sports Medicine, which is actually an orthopedics journal. So most of the papers in there are looking at sort of musculoskeletal issues, so not brain research. And it seems to have been evaluated as a slightly different, I suppose, burden of proof to most medical studies, which is really quite alarming when you're talking about people's brains. Sorry to leave that image on screen. It's quite sickening to see somebody elbow to the head by an elite athlete, if you can call the Western Bulldogs player that. And then finally, the other main sort of area which I feel there is great scope for actually engagement with somebody with a bit more statistical background is the idea of the acute to chronic workload ratio. So this is calculated as looking at the training load, a quantified measure of how much training somebody's done, divided by the 4-week average. And the suggestion, or the widely accepted belief around the acute to chronic workload ratio, is that people are more at risk of injury if the ratio is too high or too low. So the idea of it being too high is understandable. If you've done no training for various weeks, then suddenly you engage in a heavy training load without building up to it. The idea of being more at risk of injury seems quite intuitive and not very surprising. But the other extreme might be a little bit less intuitive. The idea that if you've been training at a particular level and then you slacken off and do less in a given week, that that might also increase your risk of injury, kind of slowing down. So this is the widely accepted belief about training load for injury prevention. So this idea of there being a sweet spot of not too high a ratio, not too low a ratio, is actually in the IOC guidelines for all sports, for athletes, for injury prevention. And there's now over 1,000 papers addressing this workload ratio and this sweet spot. So it usually would look presented something like that, the graph. So that's the consensus statement of the IOC, putting out the idea that you've got this ratio, which obviously it can't go below 0, because that would be that the week you're interested in, you had no training load, and it actually can't go above 4, because the current week appears both in the numerator and the denominator, of course, of the 4-week rolling average. So if you do 0, 0, 0 for 3 weeks in a row, and then a non-zero amount in the 4th week, then obviously that value for the 4th week would appear as the numerator and as 1/4 of the denominator. So you get a ratio of between 0 and 4, and they'd shown the injury risk, and this is always cited as being scientifically validated that this relationship holds. So the right-hand tail of this, the idea that ramping up too quickly and going for a heavy workload that you hadn't prepared for, increasing your injury risk, is intuitive. But the argument is that there is a sweet spot in the middle to minimize injury risk. So maybe this is me being a cynic, but whenever you see an illustrative graph which purports to be something quantitative, but there's no data points there, there's just a trend line, it's not unreasonable to ask where the underlying data set came from. Where did this trend, what was this trend actually fitted on? So if we actually go back to the original data from which this was based, well, you can see it's really ramping up at the right-hand edge. You can clearly see the highest injury risk seems to be associated with very high training loads. But around that sweet spot thing of around a ratio of 1, there's a couple of higher reports of injury risk than slightly lower. The evidence becomes a bit shakier as you look further down. And I hope I horrify you now.
You've horrified us.
Thank you. No, it gets worse. For our purposes, we've either taken the midpoint of the quantitative data was binned and then plotted at the center of the bin for the ratio, or if it was in the smallest bin, so the left-hand bin, they plotted all values between 0 and 0.5 at 0.5, and all values greater than 2 at 2. So in other words, some of those points on the right-hand edge of that should actually be plotted a little bit further to the right, and some of those data points on the left of that graph should actually be plotted a little bit further to the left. So they've actually kind of curled the graph inwards a bit. So that in itself is reasonably worrying when you're looking at fitting a curve and you've already increased the curvature of the graph. But then where did the trend line come from? They decided to fit a second order polynomial to this graph and showed that when you fit a second order polynomial, there is indeed a sweet spot, a turning point. Which is quite frankly terrifying, that the IOC's recommendations come off a simple thing of we decided to fit a second order polynomial. I mean, you could have fitted an exponential increase over that thing, because just eyeballing that, it looks like between a ratio of 0 and a ratio of about 1.5, there's no trend at all. And then once you get above that threshold, it starts to kick up. They do add, if you notice, I've left a bit of a gap in my quote before I go for the inverted commas. They note that fitting a polynomial, fitting a parabola gives you an R squared of 53%. You only get an R squared of 34% if you fit a straight line through it. Now, when we're talking about the amount of money involved in elite sport, particularly at Olympic level across all sports, all ages, men's sports, women's sports. When the committee recommendations are based on so little statistical engagement, this is worrying. Like, there is enormous potential for these studies to be done and done properly, but currently pressing the "I'll have a second order polynomial" button on Excel seems to be the state of the art here.
That's what I'd do. And I'd say there's a minimum, wouldn't I?
But
Now
by
that-
assuming
I-
rapidly, you've assumed there's a minimum. Your answer is the product of your assumption there.
Yeah.
I mean, there is a clear maximum. There is a clear that as you ramp up this ratio, the risk increases. That's definitely the case. The right-hand tail very clearly kicks up. But whether there's a minimum, whether there's a turning point, or whether it's simply kind of below about 1.5 plateaus off and becomes there's a baseline risk you can't avoid. I can't see any strong evidence that it's the curve up at the left-hand edge of that strikes me that it's more a product of the assumption that it's parabolic than anything else. I mean, if you're going to look at that, you should at least have looked at how well that would compare to fitting a functional form that didn't inherently contain a local minimum. But anyway, so there's a few of these sort of little opportunities where there's a huge gulf between the need for quantitative studies and the sort of quantitative skills going around in the field. So I just want to present these kind of ideas more as a platform of opportunity, that there is an enormous amount of data out there, enormous number of data sets, and good people gathering reasonably good quantitative data sets, which are then not really being subjected to the same level of statistical scrutiny that you would expect in other fields. So, I mean, I've worked a lot in ecology and environmental science, and particularly if any of you have worked in biomedical science, there's a long record of engagement with statistical communities. If you try to get anything published in medical evaluation, the level of statistical protocols you have to declare and publish is really, really detailed. Now, obviously, different fields have different quirks and limitations, and the inherently small samples and noisy samples of sports and exercise science present some challenges. But I don't think that's an excuse for either lowering the bar of proof without realizing that's what you've done, or just misapplying techniques. And I would say it's misapplying to say that because you haven't rejected a null hypothesis based off only 29 data points, that you have validated that there's no impact when your point estimate is 2 to 2.25 times the size. And I think the other thing to note is that when engaging in these things, there's a difference between performance evaluation in sports and health evaluations. I think lowering the burden of proof on saying, hey, if you try this training regime or this diet, it might improve your time in this race or your score in this sport by a particular margin, might not, but let's try it anyway, is wholly justifiable. If you kind of know, look, the burden of proof, I've lowered the burden of proof, I know this isn't harmful, may or may not be beneficial, let's try it. There's a difference between that where you're evaluating performance measures and when you're evaluating health measures. When you're evaluating health measures, particularly brain injuries, and looking at people's long-term cognitive function, it's absolutely negligent to not be looking at this at the most stringent definitions. You wouldn't get away with that in a strictly medical evaluation, and neither should you within a sports context. So the opportunities, the field is crying out for proper engagement with statistics in a way that the biomedical sciences have in general done, but I don't really feel that sports science has done wholly. So whilst I say this is an unmissable opportunity, I promised myself I'd limit myself to not too many weak sporting analogies or pathetic puns, but that is an impressive miss. Anyway, so I also don't want to boil academic research down to dollars and cents and kind of go, is there money in it? Are there citations in it? But there is a huge amount of money available within sports and health sciences, both at the elite level of sport and how much these broadcast deals and attendance deals are worth in terms of billions of dollars, both nationally and internationally, but also at the sub-elite level. Nearly every level of government, from councils to state governments to federal government, have a lot of money to encourage youth participation in sports. There's a lot of money and a lot of interest to get these evaluations done properly. So these are not just sort of obscure sort of pub debates of trying to quantify which player is better than another. There's a lot of serious societal impact and benefit to getting these things done properly. So I would just urge people to kind of look at this and also actually engage with sports practitioners, because the problem has been where statisticians, the statistical community has maybe been seen very separately from the sports science community. And these things have been left to develop in-house like MBI, MBD, and that this is really beneficial to nobody. It doesn't help a field to develop so separate from the statistical mainstream. It's a missed opportunity in terms of impact for mathematicians and statisticians, and it's a missed impact for sports practitioners, whether that's looking at the safety and the health level or the impact in terms of elite performance level, in terms of getting these things done right. So the opportunities are there on both sides. So I'm not just suggesting go out and hug a colleague, but go out there and actually engage with people, because it's not a lack of willingness to improve statistical practice. Everybody I've spoken to working in sports and exercise science has generally had a very, very keen ear for statistics and wanting to improve statistical practice and wanting to know more. But many people have done no more stats than what they covered in an undergraduate or possibly postgraduate degree in sports science, and so they picked up bits of stats along the way. And so that when tools come along like ready-made Excel spreadsheets where you just drop numbers in and qualitative statements come out, they're very appealing. But the challenge is for people to actually go out and make sure that the opportunities are taken by people with the best statistical mathematical backgrounds to actually have this impact. So my sort of closing remark is, do actually kind of take these opportunities because there are people out there desperate for better statistical practice, and it's a good opportunity in terms of both funding and impact and genuinely helping along a field which I feel has been sort of left out some of the academic mainstream. And on that note, I'll end on a slightly positive note. So thank you.